Hi, everybody. All right. So, um, oh dear, for some reason, Notability is reinstalling. 1 second. So for those of you who are in the US right now, it is election day today. Um, uh, as I said earlier, if you would rather watch the class later, you're welcome to not attend now, as you always are, of course. Uh, so far, it's been eerily calm out there. Let's hope everyone stays safe. Well, okay, so at least in Massachusetts, it's calm. I'm in Cambridge, which usually is pretty low key on election day. So, um, all right. Um, let's see. Chat. Okay. So, does anyone have any questions or anything they'd like to discuss before we get started? Okay. If not, let's pick up where we left off last time. I'll share my screen. Yeah, I thought about I thought about canceling class today or recording the lecture at a different time. But I'm just too nervous. So I thought this would be a good distraction. So let's let's get back to let's do some math for the moment, and then worry about everything a little bit later. Okay, so last time we were trying to prove we stated without having proved yet the following proposition. So let's let f be integrable on RD. Then there exists an epsilon. Then, sorry, for every epsilon. So 1 for every epsilon bigger than 0. So fixing f, there exists a set b with the measure of b finite such that the integral of f on the complement of b is less than epsilon. So you can think of b being, say, a large ball. 2, this is absolute continuity of the integral. So for every epsilon bigger than 0, there exists a delta bigger than 0, such that for every set E with the measure of E less than delta, we have the integral over E of absolute F is less than epsilon. Okay, so these are the two statements that we made last time, and let's do the proof. We discussed them a bit. So the proof is as follows. So these are basically going to be consequences of the monotone convergence theorem. So note that both statements are about the integral of absolute f. So we can, without loss of generality, just assume that the function is non-negative. So without loss of generality, assume f is non-negative, just replace with absolute f. So for part I, just let's let Bn be the ball of radius n, centered at the origin, and let's let f in x to be defined as just f of x times the cutoff to the indicator function, times the indicator function in the ball of radius n, so f cut off to this ball. This is measurable for every n, since f was integrable, and hence measurable, hence measurable. And note that the limit, since we're just letting this be larger and larger balls of radius n, the limit as n goes to infinity of fn of x is equal to f of x. So fn converges to f. Then by monotone convergence, theorem, the integral of fn tends to the integral of f. Right, this is just an application of monotone convergence theorem, since this fn's agree with f everywhere and there's zero outside of the ball of radius n. They are a sequence of an increasing sequence of functions. So they're a monotone sequence, in fact. So you can apply monotone convergence. Therefore, for every n large enough, we have 0 less than or equal to integral of f minus integral of f chi bn is less than epsilon, which in other words is this is equal to the integral of f times, by the linearity of integral, 1 minus chi bn, which is equal to integral of f being complement. So, and we're done. Okay, so that was just a consequence of monotone convergence. For part 2, we'll argue somewhat analogously. So again, without loss of generality, f, we can assume that f is non-negative, again, since the statement is about absolute f. And let's let fn to be equal to f times chi en, where en is defined to be the set of all x in Rd, such that f of x is less than or equal to n. Okay. And so again, by monotone convergence, there exists an n bigger than 0 such that, so large enough n such that integral of f minus fn is less than epsilon over 2, say. All right, so since the f capital N's are an increasing sequence, they converge to n. They converge to f pointwise. And so we can apply monotone convergence, so we can make this difference integral as small as we like. In particular, we can make this difference less than epsilon over 2. And now fix such an n. Now fix such an n. So fix it, pick epsilon, now fix an n large enough so that this is true. And now we're going to, so in effect, since we have this global bound, this global difference, for the rest of the proof, we can just replace f with fn. So we can now we're going to fix a small set E, and look at fn on E, which is a bounded function, importantly. Okay, so so now we're ready to start the proof, kind of. Now let E be such that the measure of E is less than delta. and delta will be to be determined. So I'm not specifying delta yet. That's what we get. That delta is what we get to pick it throughout the proof. So we'll just let E be a small set less than delta. In a second, we'll tell you what delta is. Integral of f over E is equal to the integral of f minus fn over E, where n is fixed as above, plus the integral of fn over E. All right, and this is less than or equal to, then this is less than or equal to epsilon over 2, because we know that f minus fn, the integral over all of our d of f minus fn is less than epsilon over 2, plus measure of E times n, right? Because fn is en, sorry, is a set of all x such that f of x is bigger than less than or equal to n on en. So in particular, fn is always less than or equal to n. And now, just now we know how to choose delta. Delta times n is less than epsilon over 2. We're done. Okay, so that's the proof of absolute continuity. Note, of course, that this delta that we pick in the statement of the theorem is highly dependent on f itself, right? It depends a lot on f. Okay. And now the nice thing is we can now prove the dominated convergence theorem. Dominated convergence theorem. Okay, so let fn be a measurable sequence of functions. Suppose that fn tend to f pointwise almost everywhere. Suppose that the fn's are all in absolute value less than or equal to g for some integrable function. This is the catch. G. The integral g is a non-negative function just by this condition, right? And what we're assuming is that the integral of g is finite. If the sequence is uniformly bounded above by an integrable function, then you can swap limit and integral. So then integral of fn tends to integral of f as n goes to infinity. In fact, so maybe I'll write this in fact. We have the stronger f estimate, fn minus f goes to 0. I think goes to infinity. Okay. So note that this bottom condition implies the top one by the triangle inequality. Okay, but not the opposite. Okay. Okay, so does the statement make sense? Any questions about the statement of the dominated convergence theorem? If you have a sequence bounded by sequence is all uniformly bounded by a integrable function, then you can swap limit and integral. Okay, let's prove it. Again, we've worked hard enough so that the proof is not going to be so bad. So the proof, in fact, will be a consequence of the previous theorem. So for every and the bounded convergence theorem. So for every n bigger than 0, so let En to be the set with, it says we can have two conditions. So it's all x and Rd such that one x is an absolute value less than or equal to n. So it's all x's within the closed ball of radius n, and g of x is less than or equal to n. So remember, g is an integrable function, but I'm going to restrict to the set En. And given epsilon bigger than 0, we can use the previous proposition to find an n large enough so that integral, on En complement of g is less than epsilon. Right, because En's are contained in the ball of radius n, we could just take this ball large enough so that this holds, right, outside the ball of radius n, on the complement of ball of radius n, and in fact, we can make this hold on in fact, the complement on En complement itself. Okay. All right. Yeah. Okay, so then, I'm going to look at the functions. What did I do? The functions Fn times chi En satisfy I like to do, sorry, I'm going to match these up. What have I got here? No. I'd like to. So this is true. And these are supported on set of finite measure. For every capital N. So if we fix an N, then the support of the measure of the support of these functions is bounded by n to the d, right? So constant times n to the d, where d is dimension. So by bounded convergence theorem, En we have this. So we can deduce the convergence on these sets En for every large n, little n. And therefore, Fn minus f, the whole integral, is less than or equal to the integral over En Fn minus f, which we just said is small by bounded convergence theorem, plus En complement Fn minus f, which is less than or equal to g, the integral of g on En complement. So we just use the function g on E in complement, right? The integrability of G on this outside. So this is less than or equal to epsilon plus 2 epsilon, which is 3 epsilon, and we're done. Okay, so that's the dominated convergence theorem. So we used a couple of inputs. We restricted to a bounded set on which the functions were bounded uniformly by capital N. We chose a large enough such N at the outset so that G had small integral on the complement of the set, and it's over.
I have a question.
Yeah.
Why did we need to say that the Fn times, if you scroll up, why did we need to say that the Fn times chi-n's are supported on a set of finite measure? Is that
to use the bounded convergence theorem? So in the bounded convergence theorem, you needed the functions to be uniformly bounded. So in this case, they're all uniformly bounded by N.
Okay.
And you need them all to be supported on the same set of finite measure.
Okay, great, thank you.
So yeah, so that's why we have these two indices, capital N and lowercase n. Capital N, capital N, we just fix large enough up here. Right. Maybe I should just emphasize this: fix n such an n.
Okay.
After that n, capital N is fixed, and now we just have a set of finite measure where the functions are, everything is now uniformly bounded, right? They're less than or equal to n, and the set itself is finite measure.
Sorry.
Yeah.
One more thing about, there is a bound at the very beginning of the proof of integral. The ENC, the n greater than 0 large enough such that ENC integral G is smaller than epsilon. But somehow I'm not convinced why we can do that, because En is smaller than
the ball, right? En is smaller than the ball, right? Yeah. So because okay, so how do we yeah, maybe I've messed something up. Right, so in this previous theorem here, okay. Okay, maybe I need to work a little harder.
Maybe you can say, since G is integrable, then on the ball, it's bounded almost everywhere. So you can take N to be the maximum of like the radius of the ball and like the maximum of G.
Yeah. Yeah, that's something like that should work, right? Let's think. Yeah, do I need to work harder here? Yeah, thanks, Andy. That sounds like it should be okay. Let me just think and see if I can make it even simpler.
Wait, do we know that G is bounded almost everywhere, or just finite?
Yes, no. So G, yeah. So certainly, we don't know. We don't know that G is, yeah. Okay, so I think we shouldn't just use the previous proposition, but we should use the proof. Um, yeah, we need to. Okay, so we need to work harder to. I think Andy's suggestion works. And but also Samuel's right that we need to work a bit harder to see this. Um, so okay, so we can rather than just we can't maybe rather than apply the previous theorem, why don't we apply the proof of this theorem? So let's fix those sets E in complement, and it's the ball. It's now the ball intersected with the set for which G is bounded by n. So it's a ball of radius n intersected with the set where G is bounded by n. We would still have so let's try to include the proof here. So y, if I let Gn to be equal to G times chi En, right? Then G chi En increases to G as n goes to infinity, right? And by monotone convergence theorem, there exists n such that less than say epsilon over 2. How does that look?
The thing is that two ends are, I don't know,
So forget little n at this point. This is just so forget little n. Let's just think about capital N for this this statement. This statement has nothing to do with little n, right?
yeah.
And so now ENs are some set, right? It's a ball of radius n intersected with a set of points where G is less than or equal to capital N. And do we agree that we have this that this holds, that these are this is a set of increasing function, a sequence of increasing functions tending to G. So then we can apply monotone convergence, right? With capital N, right? So capital N, we can apply monotone convergence theorem and obtain this statement, which is exactly this. Right, and so now after we obtain this integral, we're just going to fix such a capital N. That's it. And then and now the rest proof is going to be capital is we for each little n we define Fn times chi En, and now we apply bounded convergence theorem to the sequence on the sets En E capital. Samuel, does that seem reasonable? I've convinced myself, but you definitely the conclusion of the previous proposition isn't the right thing to do, but rather it's the proof.
Yeah, that makes sense.
Okay.
Thanks a lot.
Okay. Okay. All right. Okay, so this is the dominated convergence theorem. Let me go back to black ink. So the last comment is that we can also integrate complex valued functions. So complex. We're going to talk a bit about the structure of the space of integrable functions for a bit. Complex valued functions. So f, say a function from Rd taking values in the complex numbers. You can always write such a function as f of x is u of x plus I times v of x, where u and v are functions from Rd to R. And we have a definition here. Such an f is integrable if absolute f, which is defined to be u squared plus v squared 1/2 is integrable. Note that u is less than or equal to f, absolute v is less than or equal to absolute f, and f is less than or equal to absolute u plus absolute v by the triangle inequality. So therefore, absolute f is integrable if and only if both u and v are. And we define the integral of f is, no surprise, integral of u plus I times integral of v. So this is how we integrate complex valued f. They're integrable if and only if their real and imaginary parts are both integrable. That's that. And so we're then led to the following remark, which will make more precise. This set of all. So I'm gonna write this. All f from either Rd into R or C that are integrable, set of all integrable f forms a vector space. Over R or C. Okay, and let's give this vector space a name. So the vector space L1 of Rd. So this is equal to the normed space, the normed vector space L1 of Rd is equal to the set of all f measurable in Rd with an equivalent. So I'm going to write slash middle because I'm going to find an equivalence function in a second, such that the L1 norm of f is finite. So this is the L1 norm of f is finite, where the L1 norm of f is defined to just to be the integral of absolute f over Rd. And what's twiddle? So what's this equivalence relation? So note the L1 norm of f equals 0 if and only if f is equal to 0 almost everywhere, right? So the the zero element of this vector space isn't well defined. So this is why I'm not saying this is what we'll do is what we've been doing implicitly for a while is we're going to just identify functions that agree except on a set of measure zero. So so in general, so means f equals g if f equals g almost everywhere. Maybe I'll put sorry f and g are we identify functions f and g if f and g are equal almost everywhere. So the elements of L1 are not really functions; they're equivalence classes of functions, right? Where we have to identify functions if they agree on a set of measure zero, except on a set of measure zero. But now with this equivalence relation, this is a bona fide vector space. So proposition L1 of RD is a vector space. So let's let f g be in let me give myself more space. So let f and g be elements of L1. Then I AFL1 is equal to absolute A times the L1 norm of F, where A is in, for every A and C, complex number. The triangle inequality holds. This is a norm. Three, the L1 norm of F is equal to 0, just as I said, if and only if F is equal to 0 almost everywhere. So which means F is this, if and only if F is a 0 function. 4, this defines a distance. So this norm gives rise to a distance. The distance between two functions f of g is just to take the difference of f and g and compute its L1 norm. This is a metric. So in the sense of metric spaces, is a metric. Note this is not negative, and it's equal to 0 if and only f is equal to g almost everywhere. It's symmetric, and the triangle inequality holds. D. Okay, so this is a so it's a in particular it's a this is a metric space. Okay, and with a metric space, so recall the following notion of metric completeness. So if VD a metric space so via a space with metric D is complete if every Cauchy sequence converges. All right, this is a notion of completeness in a metric space. Converges to an element of V. And in this sense, L1 of RD is going to be the completion, the metric space completion of the space of Riemann integrable functions. So the L1 of RD is the completion of space of And this is expressed in the following theorem. This is called the Reese-Fisher theorem. I think this is Fisher with a C. I hope so. The vector space L1 of RD is complete with respect to its metric, the L1 metric. Okay, so remember this is what this was the this is one. So the next vector space that we're going to consider is L2 of RD, which we already saw a bit of for this for functions on the circle. So for 2 biperiodic functions on R, functions on the circle, and we saw in our study of Fourier series that the set of Riemann integrable functions under the L2 metric was not complete. The same proof is going to work we get for L1 is going to work for L2 essentially. So we'll state that in a second. But okay, let's argue for L1. Proof. So we need to show we need to take any Cauchy sequence, and we need to show that Cauchy sequence converges to an L1 function. All right, so in particular, we're going to have to find the L1 function that it converges to. Okay, so this is a little bit of a tricky argument. So let's let Fn be a Cauchy sequence. So that so it's a Cauchy sequence. So I should in L1. Which I can phrase as the Fn minus Fn, the distance between Fn minus and Fn goes to 0 as n and m go to infinity. So okay, so what we're going to try to do is find a subsequence. We're going to first try and extract a subsequence that converges almost everywhere. And also not only converges almost everywhere, but converges in norm to an L1 function. And then once we find a subsequence, we can that converges. We can use the fact that the sequence itself is Cauchy to deduce that the full sequence converges. Okay, so that's the idea for the proof. So first, we're going to look for a convergent subsequence, and then we're going to use Cauchiness at the end. Okay, so. Okay, so first, how we choose a subsequence, we're going to try and quantify. We're going to try to quantify the convergence rate of a subsequence. So we know that we have this qualitative statement. So this is one of these arguments where we're going to try and start with a qualitative statement, and then extract some quantitative statement that we can really work with. Quantitative version of this that we can really work with, and then try to, and then once we have to go back to this, we'll use a quantitative version to extract a limit, and then we go back to this qualitative statement at the end to show that the limit has to be the same that we found. So hopefully that wasn't too confusing. Let me just show you how it works. So first, step 1, maybe that's right first. Find a subsequence Fnk such that if I look at consecutive elements in this subsequence and measure the distance in L1, this is less than or equal to 2 to the minus k for every k bigger than or equal to 1. right? I can do this by cosinus, by cosinus, right? I just keep on looking farther and farther out. At the cost of passing to a subsequence. Now, since I have this quantitative rate, I'm going to define f of x to be equal to f in 1 of x plus the sum from k equals 1 to infinity of f in k plus 1 of x minus f in k of x. So this is like a telescoping. Sum, and I'll set g of x. So the idea is we're going to try and apply dominant convergence theorem. Set g of x to be equal to just taking absolute values of the sequence and using triangle inequality plus the sum from k equals 1 to infinity absolute. Okay, and so I claim that that in fact g is integrable by monotone convergence theorem. So note that integral f in 1 of x, rather actually, sorry, let me plus the sum from k equals 1 to infinity integral this is less than or equal to plus the sum from k equals 1 to infinity to the minus k, and this implies that g is integrable. So this is the point where we use some of this quantitative passive subsequence to obtain some quantitative control, because now we have some ability. So g is integrable, and the formal proof you can deduce this by monotone convergence. Theorem. And absolute f is less than or equal to absolute g, right? Because just by triangle inequality, which implies that f is integrable. I.e. f is in L1. Alrighty. So this is our L1 function. Therefore, since we have a function which is defined by this series, we know that in fact this series converges almost everywhere, right? Therefore, series that defines f converges almost everywhere. In particular, and so the partial sums are, and this is the clever, fk is f in 1 plus the sum from k equals 1 to say k minus 1 of f k plus 1 minus f in k. This is just equal to f. This sum is telescoping, right? So this is equal to f, f in k, capital K. This is a telescoping sum. Okay, and so therefore f in converges to f almost everywhere, right? The series defining f converges almost everywhere. The partial sums of the series are just given by the fnks, so the fnks converge almost everywhere to f. So if pointwise convergence almost everywhere. And now the claim, the heart of the matter, is now the claim that in fact that we have convergence to f along in L1. Okay, to see this, we're going to now use dominated convergence in the fact that G, we built this integrable function G. So we're just going to dominate by G. So see this, F and K, F minus F in K, where this is the, remember this is the kth partial sum, is just bounded K, or this is the K minus first partial sum. This is bounded above by G. Can just apply the dominated convergence theorem, since G is integrable. Which now implies that the limit as K goes to infinity, F minus F and K goes or is equal to 0. Right, so now we just hit this with dominated convergence theorem. And now we have convergence along a subsequence. We can just use Cauchiness to get convergence of the full sequence. So given, finally, given epsilon bigger than 0, find n such that for every n bigger than n, fn minus fm, L1 is less than epsilon. And then f minus fn, L1 is less than or equal to fn minus f and k, L1, and we're just going to take n large and k are really large, so that this is nk will be our m up above, plus L1, this is less than 2 epsilon. So we're just pick k large enough. K doesn't appear on the left hand side, so we're just going to pick a large enough k so that this is small enough. And then we're done. Okay, and the last thing I want to do today.
May I ask a question?
Oh yes, of course. Yep.
Yeah. Here in the Riemann integral, there are pathologic cases which violates the completion. How this line of proof is solved? These pathologic cases, can we look the proof from that perspective?
I see. So how why okay, so I guess so if we just take if we took our sequence fn's to be a Cauchy sequence of just Riemann integrable functions, right? So the issue is the issue that we're gonna resolve is the nice behavior of measure and integration with respect to taking limits. All right. And the big claim that we flew through in this proof was that this function f of x, right, is a measurable function. And in fact, that this g of x is an integrable function. So there's and that's precisely somehow the problem. So even if I took the fn's to be all Riemann integrable, there's nothing that should tell me that f should be a Riemann integrable function. In particular, right, or g, or G, let's say g, right? This is the first thing we prove is integrable. No matter how nice the fn's are, they're nicer, or well, maybe I shouldn't say that. There are plenty of examples of sequences of Riemann integrable functions for which this function g is not a Riemann integrable function. But we worked really hard to show the nice limiting properties with, first with measurable sets, then with measurable functions, so that taking infinite sums like this is no big deal as long as we have some control over the integrals of these differences. Right, we're able to exchange integral, and we prove this theorem about sums of measurable functions, of integrable functions, right? That we can interchange sum and integral with no problem, as long as everything is nicely convergent. As long as, in particular, the sum of the integrals is convergent, which is what we used in this step, right? The sum of the integral is convergent. Then we know that not only now we know that the original object itself is has to be an almost everywhere convergent process, and it almost everywhere converges to an integrable function. Does that answer your question?
Thank you very much.
Yeah. So it's all these limiting properties. The Riemann integral, it doesn't come equipped with the class of Riemann integrable functions doesn't come equipped with these limiting properties, which we're now using very fast. But if you remember at the beginning, we worked very hard to make sure that that our theory somehow behaves nicely with countable objects, countable collections of objects. Okay, so just a quick corollary to the proof. So corollary to the proof of the Riesz-Fischer theorem was if I have convergence in norm. So if I have a sequence, and if fn minus f tends to 0 as n goes to infinity, then there exists a subsequence where which converges pointwise almost everywhere to f. So this we use this in the we basically use prove this fact, right, in the proof. Right. The way you can argue here is if you have convergence in norm, then the sequence is Cauchy, and then you can extract the subsequence exactly as we extracted it before. So that's that. And I think I'm gonna stop here today. Just to keep the class short for those skipping here, so not get too far ahead. So I'll stop here. Next time we'll pick up with density so now we have this vector space of L1 functions, and where the elements are funny, right? They're equivalence classes of measurable functions, or the Lebesgue integrable functions, right? It's hard to get a hold of what this class is. Next time we're going to prove that in fact simple functions are dense in this space. It should be kind of clear from how we built it. By kind of construction, the simple functions are going to be dense. In fact, the continuous functions that have compact support are dense in the space as well. In fact, smooth functions with compact support are dense in the space. So so it's a nice L1 is a nice vector space. And next time we'll talk about L2, LP, etc. And then we'll, I think, at some point soon get back into the Hilbert space theory, but now with fully armed with the Lebesgue integral. Okay, so I'll stop there. Any questions before we go?
Sorry, one slightly silly question, but can we strengthen the corollary by saying that Fn convergence in L1 implies convergence almost everywhere?
No. You need to, it's only true up to a subsequence. You can only do this up to a subsequence. I'm pretty sure. So you can, I think. Oh, maybe. Let's see.
I mean, I have heard of something called typewriter sequence, but I don't know whether that is related.
Yeah,
to...
maybe you're right. Maybe you're right. We haven't proved something like this yet. So this is a very quick corollary to the proof, but we haven't proved that. I think that might be true. She said, if convergence almost everywhere.
I see. One more.
No, maybe we need a caveat. Maybe we need no. Maybe we need a caveat. Let me think about that. Sorry, I'm not thinking clearly. Let me think about that. I can't remember if we need a caveat or not. I'll get back to you.
All right. One more quick question. Since you have talked about the density of simple function, whatever, can we kind of talk about the separability of L1?
Sure, we can. I can mention that as well next time. Yeah. I'll discuss that together next time with the density and viewing L1 as a separable. The topology of L1, I guess, right?
Yeah.
In general, it's an ugly space. It's a pretty ugly space, but it's not like pathological.
Fair. Right. Thanks so much.
Thanks. All right. Thanks, guys.
Professor?
Yeah.
I try to have some geometric picture, and I have the following function series in my mind. We have a rectangular interval, and we are from the left, we are pushing the limit towards to the right-hand side. So when we take the differences and taking the integrals, this integral will approach to 0 in value. So this way we generate a geometric picture of functions which are closing the interval up to a point, but in the limit case it will be just everywhere 0, but some value at some point. I mean the following: we have the function which is only defined from 0 to 1, and in that interval it is like 1. Then we are pushing this series to 0 to 1/2 to 3/4 etc. It goes more, it closes more and more towards one. So in the limit case, the norm error approach to zero. But however, the function which we are approaching is a quite pathological function, which is only defined at one, which is one, and zero else. So in that point, we are losing the Riemann integral definition of the function. So this was the problem of the Riemann integral, and we want this was a specific Cauchy sequence, and we want the Cauchy sequence limit also have the nice property regarding the completion. But the converged function is not like that way. So this is one kind of pathologic example.
In the Riemann setting, right?
Yeah. I try to categorize what were the all the problems of Riemann integral. This was one of the cases I can visualize. Are there, do you have any others in your mind? For example, when we push the functions towards the infinity.
Yeah. So I mean, there is a good example in the book, or in the previous book that we in the Fourier analysis book.
Yeah.
If you remember, there was a functions with that had some logarithmic behavior. So the problems were the sequence was some truncated version of logarithm, and what was.
But we in this case we will have still boundedness criteria. Here we have completion property we have in Lebesgue sense when we have some boundedness criteria. I guess the problem when it goes towards the infinity still preserves. Yeah, I mean the functional limits when they have support regions and the value goes towards to infinity. I guess they are still problematic even in the Lebesgue sense.
Yeah. Okay. So right. Yeah. Of course. Right. So all the Riesz-Fischer theorem says is if you start with a Cauchy sequence, then you have convergence, right?
Yeah. Exactly.
Yeah. So the starting point should be a Cauchy sequence, and there was this example of a Cauchy sequence in the Riemann sense of functions in a circle. So it wasn't they weren't escaping the supports weren't escaping to infinity in the domain because they were defined to be functions on the on interval 0 2 pi or something like that. Okay. Again another one of those examples like of the type that you described.
Yeah.
So you were asking. So do I have an example in mind of Riemann integrable functions on the whole line, say, that are running away in some sense, right? With supports running away. I don't have a good example in mind in that category. I don't have a good example.
Okay, at this, I have now one working example, so it is also good. I try to appreciate more having these Lebesgue integrals, etc. So it is a theoretically good step, I guess.
Yeah. That's a great exercise is to try to come up. Try to understand some bad examples for Riemann integral. Yeah. I'll think about your question a little bit. I'm very bad thinking on the top of my head of stuff. So as you guys may have noticed. So I'll think about.
We are learning very good from you. Thank you very much for sharing your experience. Yeah, we are very happy.
Thank you, guys. Thank you. I'll think about your question though, of some good examples, or I'll try and point you to some good examples of of badly behaving sequences of Riemann integrable functions.
Yeah. Thank you very much, Professor.
Thank you. Thanks for the questions.
Bye.
Bye, guys.
Can I just ask one quick
Yeah,
question?
sure.
Yeah. So did we prove? I guess it's not. Have we proven that two functions that are equal almost everywhere will have the same Lebesgue integral? I couldn't remember if we explicitly proved that.
So I think we can go up in step. We can go up. Well, I don't think we explicitly proved it, but we can. Let's see. So we can do this for the first. The proof is easy, I guess, for simple functions. And easy for and then easy, I'd say, for functions bounded functions on support with bounded support, right? Because if we just right. Okay, so the next the next
the only issue would be the only issue I saw. Yeah, sorry.
Is it being is like you're worried about the functions being like infinite somehow, like or losing on the sets of
yeah. I mean, we know that they because we know that they are infinite. They're only finite. Sorry, they're only infinite on a set of measure 0. But how do we know that that's? So I guess my question is, if we just take the soup of bounded functions, then the unboundedness on the set of measure 0 will never cause a problem. Is that the idea?
Yeah.
Okay.
Yeah. So it's the order. It's kind of the order of it's how it's so that you have to know this is a careful way in which we defined the integral of functions on an arbitrary set. So like let's forget about let's think about non-negative functions on an arbitrary size set. First, we have to consider all G that are bounded and the G that are less than or equal to F bounded and on a set of finite measure. And once you only start working with in this class, you can ignore sets of sets of measure 0, right? And so you do this ignoring before you take the soup. So that's the crucial part.
And you know that's okay because as long as it's bounded, then a set of measure 0 will never affect the Lebesgue integral.
Exactly. Yeah. So at that stage, you could just ignore sets of measure 0 because once you have a uniform bound on the function, it doesn't. That doesn't. That set of measure 0 can't contribute, right?
Okay.
So. Yeah, and then you only define the integral of a function that's possibly unbounded by taking such a soup, by taking soup of all such functions. So since you can throw out sets of measure 0 or ignore sets of measure 0 in the first stage, they don't come up then at the latter stage, and it's a sleight of hand almost because I see exactly what it's you feel uneasy about it, right? It's like you're worried like, oh well, what if this like the function is identically equal to infinity on this set of on this small set of measure 0? How do I know that this I should know the size of infinity and the size of 0 somehow, like the size of the set versus I don't know how to multiply 0 times infinity.
Yeah.
Right?
Intuitively, it could be a problem. Yeah.
Yeah. It's just so it's a sleight of hand in the way we define it, and that we dismiss with this ambiguity before dealing with that class of functions where this can happen. So yeah,
okay.
It stuff with the infinite is always a little bit easy. It's easy to feel uneasy about it, but that's the answer.
Okay, that does make sense. Okay, thanks. And actually, can I ask a really small question about something at the end? I was just when you talked about the L1 being the completion of the space of Riemann integrable functions. Does that mean that L1 has to be the smallest possible set containing Riemann integrable functions that is also complete, or
complete is a vector space.
yeah.
So I think often with okay, so if you remember with the so the completions are somehow unique. Um, uh, but they depend highly on the metric that you choose. So you sort of complete with respect to a metric. And if you remember, like with the there's different ways of completing there are different metrics you can put on spaces, and then you get different completions at the end. But once you fix a metric and complete with respect to that metric, then the resulting thing you get at the end is in fact unique. So it's the not just the smallest one; it's sort of the unique object somehow.
Oh, okay. So it's a little bit different from, say, oh, sorry.
Do you remember like the real numbers have this property?
Yes, I do remember.
Yeah.
And it makes sense that you can't add anything to the real numbers, obviously. But that's not so obvious to me with the space of functions. But
it's like
I can believe it.
But it's a bit of an it's a bit of an abstract metric space argument that somehow it's not. It's like this is a abstract argument about metric spaces. Somehow it doesn't really care too much what the metric space is. I guess.
Okay.
It tells you this, but yeah, it's unique in fact.
Okay. That's so. I just to make sure I understand. So it's a little completeness is a little bit different from closure under other operations, because in general, if you're closed under an operation, doesn't mean that there's only one set that.
Yeah.
Like you can be closed, but you can also increase the set and still be closed.
Yeah.
Right. But you're saying completion is complete.
Yeah, I think so. Yeah.
Okay. I understand.
Yeah.
Okay. Okay. Thanks.
Cool. Thanks. Good questions. All right. Talk to you soon.
I'll see you on Thursday.